So I'll be talking about compressible fluids, entropy hierarchies, and flocking. And this is combining sort of two works that we did a couple of years ago, with the first with Peter Constantin, Nguyen, and Federico Pasqualotto, and then after with Peter and Roman. The focus of the talk will be on the latter work, but they discuss similar models, so we'll talk about both. Okay, so the class of equations that we're going to consider are these one-dimensional compressible Navier-Stokes type models. So I'm sure everybody here is familiar with them, but mass conservation is encoded by the continuity equation for some non-negative density rho. And then the momentum equation for the momentum rho u is forced by a pressure, and there's some dissipation operator, which I'll discuss more in a second, and possibly external body forcing. So the first point is that the pressure closes the system once you declare some given equation of state relating it to the mass density of the fluid. In this case, we'll consider just power law relationships rho to the gamma, which is sort of standard from the point of view of compressible Navier-Stokes. They arise, for example, in the description of an ideal gas, but also, as we'll see, this type of pressure relationship arises naturally as effective descriptions of more complicated system in higher dimension. So the two types of, we'll consider two different types of diffusion operators in this talk. One is sort of more conventional local dissipation, which takes the following form. So it's a total derivative of some viscosity now allowed to be depending on the mass density times the gradient of the velocity. And again, we're going to consider viscosities of power law type, which arise once again naturally in different contexts. And together with the pressure law, this closes the system and describes, for example, ideal gas in an isothermal state in one dimension, or it serves as an effective model for shallow water waves coming from incompressible fluid in some regime, which I'll discuss, and slender jet equations that govern the formation of drops, again, dealing with an incompressible fluid, but described effectively by a one-dimensional compressible model. The second family of diffusion operators that we'll consider go by the name of singular Cucker Smale models, which were introduced by Roman and Eitan in 2017 as in the context of flocking models, so hydrodynamic description of agents communicating and flocking. These singular communication kernels have to do with sort of promoting local interactions more strongly than global, although of course it's a non-local operation. And what they show is that in this setting, this D ends up being a dissipation, which involves just the usual fractional Laplacian, which I denote by L to the S, just S derivatives. And it has this explicit integral kernel representation if you're working on the torus, which we will for the entire talk. Okay, so I'll say more words about this shortly. Okay, so let me tell you a bit more about these examples, focusing on the reduced models, not the molecular fluid models. So the first is shallow water waves. So imagine you have some incompressible ocean with a free surface and some bottom topography, and you're considering a regime where the depth of that layer, the ocean, is much, much smaller than the extent. And in this regime, the dynamics simplify by one dimension effectively if you consider averaged sort of depth averaged quantities. And the topography just enters parametrically into this reduced equation. Okay, and so you want to just understand motion of, say, water in a lagoon. Okay. The simplest such setting is if the if the bottom is flat and the water is just sitting on top and two-dimensional in the sense that it has already a certain symmetry, then the description should be effectively one-dimensional, where you only keep track of the velocity transverse and the height. And indeed, Gerbeau and Pratham showed that in this limit where the characteristic dimension of the vertical is much smaller than the horizontal, this system, which is originally an incompressible system, is governed by a one-dimensional compressible Navier-Stokes equation, where the role of the density is played by the vertical extent of the fluid, the height of the free surface, and the velocity is some vertical averaging of the horizontal velocity of the original flow. And what appears here is that the height of the fluid acts as an effective viscosity in this description. So you can just map this equation onto the general class that I started off describing. The pressure law is quadratic and the viscosity is linear in rho. Okay, so it's one particular case of those exponents, gamma and alpha, that I described at the beginning. And the natural question here is this a well-posed problem for all time? So, and we'll discuss that. Second phenomena that's describable by this type of model is an interesting one arising in the formation of certain type of singularities. Namely, if you have a thin neck of fluid, say when you turn on a faucet and you have this column, axisymmetric column of incompressible fluid like water, then in a regime when it's about to form a drop, so asymptotically when the neck radius gets very small, an effective description for the behavior there can be given in terms of one of these compressible Navier-Stokes systems. So this was done in the 90s by Eggers and DuPont, who derived such a reduced model. It takes this form where h is the neck radius and u is again the transversal velocity down this neck. So z is just the height from the faucet. And in this asymptotic regime where they assume the neck is getting very thin, they show that these variables follow these equations. So if you take the mass density to be h squared, you can again map this system onto a compressible Navier-Stokes system where the pressure is actually negative and the viscosity is positive and linearly proportional to the density. So this negative pressure is actually a very important point. So the compressible Euler system, if you didn't have viscosity, would not be well posed. And this negativity of the pressure is believed to be the driving mechanism within this reduced description to say how the drop forms, which, by the way, is just the statement that the height goes to 0. So at the level of the compressible model, the question is, does it form a vacuum in finite time? And related to this point was a conjecture of Peter when this model was originally derived, where he just asserted that prior to any vacuum formation, so as long as the neck didn't pinch, the solution should be continued classically, namely that, H being positive is a continuation criteria for this system. So that's another motivation for studying these models. And just to show you that this description works pretty well, here's the experiment overlaid with some numerical simulations by Eggers and DuPont. And you can see that the neck, described by this one-dimensional model, appears to be quite faithful to the actual behavior of the drop. And it's conjectured that the singularity should be of a self-similar type. But what makes it difficult to study is that it's not symmetric and the profile is not explicit. Okay. So the final set of examples I'll discuss are those that arise in the context of emergent behavior. We all know that when you see a collection of agents like birds or fishes, or even views on the internet, there's some phenomena that over time these agents tend to align in their actions. So in the context of birds, they tend to form some type of coherent structure, this blob that move at some constant speed, maybe a V shape or something like that. And one wants to model how this happens. So Cucker and Smale in the early 2000s devised a finite dimensional model for this behavior where you have n agents whose velocities are V, and their velocities can change via some binary communication with the other agents. So there's some kernel here that allows xi to see xj and modify its velocity accordingly. This kernel is called an influence function. Originally in this work, it was some positive bounded function, and they simply studied the resulting dynamics. Now, you can encode this system in an empirical distribution function. So you just put Dirac's in the phase space. And so what we're after is a continuum description. So Han Tadmore described a kinetic model, so a mesoscopic model for this finite dimensional system when n is large. And if you start with a monokinetic ansatz that says that the velocity is deterministic in the sense that it reduces to just some space-time field, which, by the way, can be justified. So this was work of Kang and Vasseur and Fagali and Kang. If you assume very strong local alignment, then this mesoscopic description reduces to a hydrodynamic one, where the fields that you keep track of are only the mass and momentum. So it closes in terms of those two moments of the distribution function. And yet again, you get some type of one-dimensional compressible equation where you have mass density and momentum now influenced by some non-local interactions that represent how these agents see each other and change their velocities. Okay. So before we consider the actual models we'll study, let me just say what flocking means precisely in this context. So there's this intuition that agents should sort of crystallize into some shape and then travel with some given velocity in unison. So you can consider the state then of flocks as just being collection of constant velocities and densities which are of traveling wave type. So just moving with that constant velocity with some given shape function. And then you say a solution of this system flux, provided that you have some convergence in some suitable topologies to an element of this flocking state F. So you have some convergence to some object in there. And what that corresponds to is this alignment process where, so the topology X will usually encode some weighting by the density. And this convergence to a constant is just saying that on the support of the flux, so wherever the mass density is positive, the relative velocities are all going to zero. So the objects are traveling in unison. And in fact, it's actually easy to see for these models what that final velocity has to be, because as they're a compressible fluid system, they conserve total mass and total momentum. So if you converge to a constant velocity, it must be the one that just is read off by the data as the ratio of the momentum to mass. So this part of where you flock is clear, but what's much more difficult is to understand the structure, the end state of the shape for the density. Okay. So in this talk, well, so that model has been studied at great length, and I'll discuss some of that. But in this talk, we're going to study a model which has an additional term, a pressure, just the derivative of the density here. And this term arises from considering a different closure at the mesoscopic level. So instead of monokinetic, you have this Maxwellian closure. Now the velocity is not deterministic, but is some Gaussian. And this ansatz gives rise to this new term. And so now it fits again within our framework of a compressible Navier-Stokes system, but with non-trivial pressure. The previous one had trivial pressure. And furthermore, we're going to consider not smooth influence functions phi, but rather some singular ones, which involve, as I said before, the fractional Laplacian and have a specific commutator form. These are the family that were derived by Roman and Eitan, and they describe just weighting more significantly local interactions of birds seeing their neighbors versus seeing, the boundary of the flock. So somehow a more realistic description in a way of flocking. Okay, so the questions for this model, the usual ones. So first, is it true that singularity doesn't occur unless the flock breaks up? That's the analog of Peter's question, but for these flocking models. Next, is there global regularity in some contexts? And finally, what's the long-term behavior of these models? Okay, so now just some words about prior work, and I'll start with the compressible Navier-Stokes system, in particular focusing on the case where the viscosity can depend on the density and degenerates as the density goes to zero. So some really groundbreaking work in this area was by Bresch and Desjardins, where they constructed a new mathematical entropy. They discovered a new entropy for this system, and they used it to prove global weak solutions in various contexts, first with some additional friction term, and later this friction term was removed by Millet and Vasseur. And so you have a result, in fact, even in higher dimensions, that they're global weak solutions and they allow for vacuum. Okay. Then without vacuum, later, local existence of smooth solutions was proved by Bui, Li, Pan, and Zhu. And small data global existence in 2 dimensions. So if you perturb around zero velocity and constant density, you have global solutions even in 2D. And the only large data global existence results that I know about, there are probably some more, but Millet and Vasseur in 1 dimension prove for some range of degenerate viscosities and some range of pressure laws that you have an all-time solution. And this range notably excludes the shallow water model that I started by motivating discussion. And later, actually the same year we published our paper, Boris Haspot proved in that case global regularity, and subsequently in recent years improved this type of result, allowing for less smooth initial conditions. For the non-local models, so these are the flocking models, Tadmore and Tan in 2014 proved global existence for weakly singular systems. There's some conditional existence based on some property of the data I'll mention a little later in the talk. And is followed by work of Carrillo et al. And then small data for any dimension for singular systems, which are the ones that we're considering here, was done by Roman and Danshan et al. In recent years. Then Roman and Eitan introduced these singular kernels with commutator forcing and established well-posedness in 1 dimension when there's no pressure. This is the first model that I showed, corresponding to monokinetic ensembles instead of Maxwellian. And Trevor Leslie extended their analysis to include forces. And alignment was also discussed in this context where you converge to a constant and you approach this type of traveling state that I described. And this was again extended by Xu and Tadmore for forces. Okay, so now let me tell you about some of the results. First is this first work with Peter, Hui, and Federico that concerns only the local dissipation models. And this is the continuation criteria based on no vacuum. So if you have some ranges of parameters, don't pay close attention to what these ranges are. In fact, I'll soon improve them. But the point, if you have some ranges of parameters, then it suffices to control the mass density away from 0 to continue as a classical solution. And the point here is that we allow also for negative pressures in some appropriate range of the viscosity and the pressure law, which therefore resolves this conjecture of Peter concerning the slender jet. So indeed, for that drop formation model, you can't have any type of breakdown before you have pinching. And what remains to say is whether or not that model can really describe the phenomena of formation of drop. Okay. So I'm not really going to talk about how this is proved in detail, since I'll give an alternative proof with the one with Peter and Roman. But just one word about it is that we regard this system as being forced by the derivative of this quantity W. So W just includes the pressure term and the viscous term, and we term this an active potential. Point is now the system is just written like that. And what's special about W is that it satisfies some forced quadratic heat equation with a less degenerate viscosity. So you divide by rho here, so whatever degeneration mu had is reduced for the W equation. And that allows us to consider these ranges of degenerate viscosity, which are wider than the ones previously done in the literature, just by doing energy estimates on W and rho and recovering information on the derivative of U from W. Okay, so that's all I want to say about that proof. So then after, with Peter and Roman, we proved the same type of theorem, namely continuation based on no vacuum, for a much wider class of models that includes local dissipation and or non-local dissipation. So of these two forms, one arising in flocking, the other arising in these models I discussed. We extended the range that the previous theorem could apply to greatly. So just any viscosity law with positive or non-negative exponents, and any pressure law bigger than 1, or if you want to include the pressure law as just proportional to the density, then you have to have slightly higher exponent for the viscosity. By the way, gamma equals 1 is exactly the case of the pressured flocking model. So the model where the Maxwellian is assumed gives rise to the gamma equals 1 case. So this is an important range. And so that's for the purely local. If you have purely non-local, there's a range that includes all gamma as long as you have strong enough dissipation. And you can also do mixed case. And the reason why you can do mixed case in this theorem is interesting. It's because in some sense, the way the local and non-local dissipation interact is constructive. Okay, and so this theorem is proved with a new technique, which we call entropy hierarchies, that both somehow explains the Bresch-de-Jardin entropy in a clear way, but also shows how you can make use of that idea to propagate higher regularities. So here's our system. I just keep dissipation operator general and I set the force to 0. The point about the two types of dissipations we consider, both local and non-local, is that there's this sort of magical quantity Q, it's different for each, such that the transport of this Q exactly gives you the dissipation divided by the mass density. So you can write this object as something that's transported if you weight it by the density. So in the local case, this is just some object involving the viscosity and derivative of density. In the non-local case, it's this integral operator on the density. It's just a calculation to see that indeed this is true for both those things. But now the reason why this is insightful for this equation is that you can introduce a new quantity x, which is just the velocity plus this q, which relates to the dissipation. And x is just transported up to a force that involves just the pressure. So you have some pressure law, h is called typically the enthalpy, and x would be transported purely if there were no pressure, And if there's pressure, it just has this forcing. Okay, so now here's our system. And we want to exploit this structure to try to derive some dissipated quantities and then this higher order versions of them that can control regularity. So the main insight is that if this pressure were not there, then you would have just an object that's transported and an object that solves continuity equation. And a simple calculation shows that the associated energy, just rho times that transported quantity squared, is conserved by this system. Okay. Now, in our case, since this is not identically zero, this is not conserved, but rather it's the work done by the pressure on this variable x. And x has, again, the sum of two things. It's the velocity and it's this magical q quantity. And so this just has these two contributions. One of these contributions, the one with the work done by the pressure on the velocity, is can be absorbed as the time derivative of a quantity we call pi, like a pressure potential. So this is a standard thing in compressible Euler literature. So the time rate of change of this pressure potential gives you exactly the work done by the pressure on velocity, so that you can combine this pressure potential together with this kinetic energy to give you some conserved energy for the system if there were no dissipation. Okay, so you have the usual energy, kinetic plus potential, and for the Navier-Stokes system, that's dissipated by the action of either one of these local or non-local dissipations. And what this calculation shows is that there's another quantity, which is called the Brèche-de-Jordan entropy. This is what they discovered, which satisfies an evolution forced now only by the action of Q on Px, or the work of pressure on Q. And what's remarkable is that in all the cases that we discussed, this is actually non-positive. It's a dissipation. So Brèche-de-Jordan discovered that this was dissipation in the local models, where you just compute what this is and you find it's negative of something that's positive, provided that mu and p prime are positive functions. So for some range of gamma, the pressure law, and alpha and any positive viscosity, this is just a dissipation. And this holds in higher dimensions also, and has become a very important tool for studying these types of degenerate viscosity Navier-Stokes equations. Now, in the context of the non-local dissipation, you can just, again, compute what this is, and you find, once again, it's a non-positive thing, where now the influence kernel depends on the state, but is strictly bounded away from zero. So it's really acting as a dissipation. And this gives a new entropy in the context of these flocking models. Okay. And as I said, the reason why we can treat the mixed case in the way that we do is because if you look at if you look at this quantity that shows up when you square x, and it involves both local and non-local dissipation, there's a cross term, the interaction between the two. And a calculation shows that, again, this cross term has a good sign. So it's a positive contribution. So even the interaction of them provides dissipative mechanism. Okay, so now what's the idea? Well, first we can just gather what we know from the evolution of energy and entropy. The entropy gives control of x, provided that the density is non-vanishing. So you have L2 in space, L infinity in time control for x, if you can divide through by the density. And since x is comprised of velocity plus this q quantity, and you have some information on the velocity from the energy, you can use the Brèche-de-Jordan entropy to control just q in L2. And Q, in the case of just the non-local model, so I'll just focus on that for the sake of simplicity, tells you information about S-1 derivatives of the density in L infinity. So you get some a priori information about density from the Breshter-Jordan entropy. And you also get corresponding L2 in time information from the dissipative term, as usual. Now, if S is bigger than 3/2, which we'll always take, then you deduce from this information that in fact the density is bounded just by embedding. And so just from the first order entropy, you find that the density is some bounded function, which has S-1 derivatives in L infinity. HS-1 in L infinity, and some information on dissipation, and the usual information. You don't gain anything more about the velocity from the first entropy. Okay, and these estimates assume that the density is bounded away from 0. Okay, so we want to prove this continuation criteria. Okay, so now how do we proceed? Well, we note that if you take the derivative of a transported quantity, then it itself solves a continuity equation. Okay, but in actuality, we have this force, which is the enthalpy. So it's continuity equation plus something that's forced. Now, if you have an object that satisfies just continuity equation, then if you divide it by the mass density, which also solves continuity, you would get a quantity that's transported. So y, which is this x dx of x divided by rho, would satisfy a pure transport equation if there were no pressure. And therefore, we could repeat the same argument that we did before with x and construct a conserved energy for y, which is just rho y squared. But again, here, since we have some forcing, this energy evolves according to the work done by that force, which we have to sort of grapple with. And just a quick remark, y is related to the so-called E quantity that arised in the context of these flocking models. And for smooth kernels, you have some conditional global existence statement based on the initial values of these E quantities, but I won't talk about that. It's in references here. Okay, so we have this evolution for the energy of y. And just like in the first order entropy, we want to try to construct some pressure potential that absorbs the most singular part here. So it looks like you're losing some derivatives. You have two derivatives of rho on the right-hand side. And ideally, we'd like to absorb that worst term as the time rate of change of some potential. And so indeed, you can do that. So there's pi1 is this potential whose derivative just compensates exactly the highest order derivative term that you would get on the right-hand side. So by analogy with the Breshter-Jordan entropy, we form a new quantity, which is the energy of y, involves a derivative of x, together with this new pressure potential, which is a non-negative thing. And now this is not going to satisfy conservation or a dissipation, but rather there'll be terms on the right-hand side involving lower derivatives of rho, which will be controlled by previous information from the first entropy. So think of it as just satisfying some ODE with residual terms. Okay. So then again, using the estimates from the first entropy, we find that H1 satisfies this differential inequality. There's some dissipation here that you gain each time actually from this pressure potential. There's some dissipation term. And therefore, this implies the uniform bound on this new entropy H1, so using the previous information. And from that, you can get information about the different quantity, because so again, if rho is bounded away from 0, then you get information on y. Y is just the derivative related to the derivative of x, which carries information about derivative of u and derivative of rho, but you use previous information on rho. I mean, actually, so this information on rho comes from exactly this pressure potential, because again, you have, this is like one derivative in L2 uniformly in time is controlled by pi1. So using that information together with what you know about y, you can deduce information on u. So you just invert some derivative, you get that u is in H2 minus S uniformly in time. And so you can improve a little bit the a priori estimate, again, assuming non-vacuum. And now you just continue. So we have an algorithm now. So y was almost transported. Its derivative satisfies continuity equation up to a force. Divided by rho, it's again almost transported, but with some forcing that depends on the pressure. And now form an entropy, which involves the energy of this quantity z, now one derivative of y, two derivatives of x. And you can absorb the most singular term here, once again, by a new pressure potential that involves now two derivatives of rho. You once again get some differential inequality that uses the a priori information from the previous two entropies now, and you gain a little bit more regularity. Okay. So this can just continue, and the general form is you take, you have Zn, which is roughly speaking, n derivatives of u and some derivatives of rho. This is the kinetic energy part of this entropy. Then there's this corrector that absorbs the most dangerous term on the right-hand side arising from the pressure, which takes the form of two derivatives of rho to the nth power, with these other factors. And bootstrapping the previous information from the lower entropies, you can propagate as much regularity as you started with. So you can just, so under the assumption of no vacuum, you can continue the solution classically. Okay. So just a remark, this type of no vacuum continuation criteria can be used easily to prove global existence for some models. This argument is essentially that of Millet and Vasseur. If you have a local dissipation with some fractional power less than a half, then what you gain from this, from control of that x quantity in terms of this object Q, exactly tells you that rho can't vanish, because you have some negative power of rho here in H1 dot is controlled, and then you can control also the mean of rho because of mass conservation, and you deduce therefore in fact that you have a priori no vacuum. So this continuation criteria is useful for proving like a very large range of singular dissipation models with local dissipation have global existence. Okay. So unfortunately, that range of alpha does not include the shallow water, which has alpha equal 1. That was proved again by Boris Haspot, but also a consequence of our theorem with Peter, Hui, and Federico, where we cover some now larger range of degenerate viscosity and pressure that in fact does include the shallow water equation and gives some explicit bound on how the density can degenerate as time goes to infinity. I think in interest of time, I won't actually show the proof, but it's quite simple. And once again, it uses this quantity x that involves u and that q object, which for this model turns out to be just the derivative of log rho. Okay, so the final thing I wanted to discuss is flocking. So now we're taking purely non-local models. So this is representing some hydrodynamic limit of these Cucker Smale models for interaction of agents. And we recall the energy and the entropy of this system here. And now with Peter and Roman, we have this statement that if you have weak solutions that satisfy entropy and energy inequalities, in particular, if you have just global strong solutions, then you have a certain flocking, okay, certain type of flocking, rather weak sense, but still flocking. So what is it saying? It's saying that on the support of the density, which in our theorem is going to be never zero, so supported everywhere, the velocity is aligning. So the relative velocities are going to zero with a certain rate, log t over t. So not very fast, but certain rate. And the density is converging to a uniform. So I just want to highlight this 1 second. Unlike the case where you crystallize into some traveling wave shape, which happened if there was no pressure in the system, in the pressurized flocking model, so with this term, which again arises due to some Maxwellian closure at a mesoscopic level, you don't converge to a traveling wave shape, but rather you just uniformly spread over the domain. And so this is the flocking statement for these pressured systems. And just wanted to say that Choi proves a stronger flocking statement, but under a condition, which is uniform boundedness of the velocity. And there's no a priori reason why this should hold for this system. But in his context, he gets stronger, like strong flocking. Okay. So how does the proof of this work? Well, just using the entropy and energy inequalities, the first thing to notice is that from the energy, we can end up getting a differential inequality that shows some decrease by noting that first, by conservation of mass and momentum, this object can be written as the total energy minus some pressure potential. And this object bounds above minus this one just by taking the smallest this singular kernel can be on the torus. It's bounded below. So you just estimate this by the energy minus some pressure potential. So we have some inequality like that where F involves pi 0. But we can actually control pi 0 from the entropy dissipation. So entropy dissipation bounds above the deviation of rho from unity in L2, which in turn bounds rho log rho, which is exactly the pressure potential when the pressure is a linear function of rho, gamma equals 1. So thus we have that this quantity is integrable because the entropy dissipation is integrable in time. And so we have entropy is forced by some L1 function. And therefore by Duhamel, we can just write representation formula for the solution. Okay, so why does it go to 0? Well, if you look at a sequence of times whose increments grow like logarithm of m, then along that sequence, which by the way means that each time is roughly like m log m, the contribution in a range of on a certain increment of this force has to go like 1 over n. Just think of m and n as being the same. So basically the amount of work the force can do on these increments that are going to infinity has to go to 0 at a certain rate. Otherwise, this wouldn't be integrable. And therefore, we can just break up the action of the force onto regions, just onto different regions, and show and just bound the size of how much that can increase the energy. Okay, so here it is. The leading order term is just the 1 over n term, that bound that I just showed you. And 1 over m because of the way the times were defined, is roughly log t over t. So what this argument shows by continuity of the energy is that the energy is going to zero like log t over t. Okay. And finally, the César-Kullback inequality gives a bound from below of this pressure potential by rho minus 1 and L1 square. So what that means is that the energy, which contains both the kinetic and the pressure potential actually going to zero, tells you that in the L1 topology, rho is approaching unity, and in this weighted L2, the deviation of u is going to zero. Here, we're assuming for simplicity that the net momentum is zero, so the velocity of the limit is just trivial. Okay, so that's all I wanted to say. Just to recap, for a wide class of models, non-vacuum is a continuation criteria, and this can be useful for proving global regularity, since for many such models, the dissipation itself guarantees an a priori lower bound on the density. And for others, namely like the shallow water equation, there's some argument required, but you can establish that. It also works in the case of flocking models and can give global existence in certain ranges. And finally, yeah, so we showed this L2 flocking statement for the pressured case, which corresponds to qualitatively different feature. Instead of crystallizing into some flock, you uniformly spread over the configuration space. So the density just approaches 1. And in the future, we would like to investigate whether or not this method can be useful in higher dimension. So as I said, the Brewster-Jordan entropy holds in higher dimension, but it's not clear at the moment that this method can be used for higher order entropies. It would be very interesting to investigate also this finite time singularity question for this Slender jet equation. So does that model really describe the singular phenomena of drop formation? And finally, the statement that I gave at the end about weak solutions satisfying entropy inequalities flock is, at the moment, we don't have any way to construct weak solutions satisfying those inequalities except by constructing global classical solutions. So is there a more general construction of such weak solutions that exhibit the flocking that I discussed? Okay, that's it. Thank you.
Well, thank you very much, Theo, for a very interesting talk. So let's start with questions on how we proceed. Are there any questions?
There may be some hands raised. Oh, yeah.
Yes.
Yeah. Okay.
Hi, Theo. I have a quick question. So, in the case of the drop formation, if you use, if you replace a Newtonian fluid by viscoelastic material, you can have some very interesting effects. Do you see any of this being able to be adapted to some simple models of viscoelastic fluids?
Yeah, that's a really good point. I think so. I have to think about it a bit more deeply, but I've seen some discussion of those models in the context of these slender jets. So yeah, that's a great idea. I don't know off the top of my head, but yeah.
Thank you.
Okay.
There are 2 attendees with raised hands.
Oh, really? I didn't see.
Yes.
Let me see how. Ah, okay. So sorry, it's somehow. Please, Stephen Watson.
Thank you. Can you hear me?
Yes.
Yes, yes.
Ah, super. I'm interested in the point-wise estimates for the one-dimensional situation you referred to,
Mhm.
and essentially the existence uniqueness result in detail. So what's the sharpest known result on an a priori estimate on the density from below for the 1D problem with these types of degenerate viscosities?
Yeah, so I mean, it depends a lot on what range of parameters you're considering. So if so the argument of Millet and Vasseur that I recalled was that if the density was like rho to some power between 0.5, then from the Bresch-de-Jordan entropy, you gain an a priori bound on the density away from 0. So L infinity of 1 over the density is controlled. That's true for that entire range of local models. In our paper, we give an alternative range where that argument doesn't work, and yet you can control the density away from 0. And that argument makes use of the transport type nature of this X equation. So
yeah, so maybe that was my follow-up, because I was trying to map it. Maybe this also relates to Anna's question, if I could. So in viscoelasticity, in the Newtonian type, for the one-dimensional problem, the analysis that's generally carried out is in the Lagrangian representation. So that, I guess, maps to your transport view. Yeah. So in some sense, what I was trying to in my mind do there, but I couldn't quite chase it all the way through, is to sort of map those known a priori estimates from that viewpoint to the methodologies you're using here.
Yeah, I think they should be closely connected. So I mean, because so aside from those situations where you just get it for free from the energy, you really have to make use of the transport structure, which could be thought of as just doing Lagrangian. Yeah.
If I could, I'll just remark. So the name that's given to the approach there, it's adopted the name the Pago transform. So this goes all the way back to work of Ball and Andrews back in '78, and then that was formalized in the semigroup setting by Robert Pago. And so that ODE structure that comes out is I think it's closely related.
Oh,
to what
can you repeat the name, because you broke up when you were saying it? Sorry.
Oh, sorry. So the representation of that argument, I think, in Lagrangian frame would be what's called the Pago transform.
Okay. I'll look at that. Yeah, thank you.
Yeah, but thank you. Great talk.
Thanks. So the next, there is a participant with which is marked as LGXChem. So I don't know the name. Please. Yeah. You have to unmute yourself.
Okay.
We don't hear. Any other questions? I probably have a question. So I wonder about the origin of these different entropies that you have. Do they have an ideal situation when they are really conserved?
Yeah, well, so yeah, if you didn't have dissipation, it just reduces to the energy of the compressible.
All of them reduce to the energy.
Yeah.
So all of them are reduced to energy, and then when you put dissipation, it becoming different balance laws in a sense.
Exactly. Yeah. Yeah. So I don't actually know a physical interpretation for that object. It would be interesting. Maybe somebody does, but I don't know of a physical manifestation of why that thing is entropy. But yeah.
Because physical interpretation usually comes from ideal situations. So if they all equal.
Exactly. Yeah. They're all equal.
Okay. So
maybe I can add to this to Alexei question.
Yeah.
Can you hear me?
Yeah.
Yes.
Yeah. Okay. Because it's kind of interesting, because the zeroth order entropy, right, is the classical Bresch-de-Jordan. The first order entropy is by now also classical E quantity, which was introduced by Carrillo, 8 and Tadmar and 10. So that plays a role as a topological entropy, because in the ideal situation, when there is no pressure, it controls how much the limiting flock deviates from the uniform state. So how much disorder there is in the flock. So Alexei's question is very interesting, because maybe there is interpretation to, every tier of these entropies, some physical interpretation. So that would be something to investigate for the future.
Yeah. Thank you.
Yeah.
Some other people raise their hand.
Well, it's actually the same two people, but please talk if you like.
Yeah, if I could then, Theo.
Yes,
so
please.
one other question about the degenerate viscosity. If you couple the viscosity to additional fields, I don't know if you have examples or models of that type, but I'd be interested in whether you've got models of that type and tried to carry out this analysis with that coupling, because the structure of the problem becomes, I think, much more challenging for the pointwise a priori estimate in that case.
Yeah, so I mean, a canonical example of such would be the real compressible Navier-Stokes system.
Yeah, that's
where,
right. Exactly.
Yeah, I don't know. I haven't thought too much about that, but certainly it makes everything much more complicated. I don't know of an analog of this Brecht-de-Jordan entropy in that setting in general. And there's also a lot more freedom when you incorporate internal energy and you allow for more general equation of state. So it's a very good question. It deserves some thought.
Yeah, I mean, the framework of thermal viscoelasticity is the most general framework for that. And there's a relatively robust theory in one space dimension, provided the viscosity is temperature independent. There are some efforts to make progress with temperature dependence, but they're not complete theories yet.
Yeah, yeah, it's very interesting to look into that.
Super.
Yeah.